Sudhakar Chaudhary from the Department of Mathematics, Institute of Infrastructure, Technology Research and Management, Ahmedabad, Gujarat. And he will be talking about this finite element method for parabolic non-local problems. Yeah, please continue.
Thank you for your kind introduction. Basically, in this talk, I will discuss about the numerical solution of parabolic non-local problems. What I mean by non-local problems, I think in our previous lectures already we have, heard about this term, non-local problem. So I will again, discuss about some special type of non-local problems and how to find their numerical solution. This is our main talk, basically task here. So this is the outline of my presentation. First is introduction, and here we describe about our non-local problem and what are the applications and what are the difficulties when we go to solve these type of problem numerically. Then we consider the weak formulation of our given problem. Then we go for semi-discrete and fully discrete formulation of the given problem. And here we also derive the a priori bound and a priori error estimate for the semi-discrete and fully discrete solutions. Finally, we will confirm our theoretical estimates via one numerical experiment. So, first of all, I would like to discuss what is the difference between if we take simple partial differential equation and if we take a non-local partial differential equation. We know that if we consider a partial differential equation, here basically we have a relationship between the dependent variable and its derivative. So in order to if we say that this partial differential equation holds a point, it means that we require value of the dependent variable in the neighborhood of that point. However, if we consider this non-local partial differential equation, it is completely opposite. If we say that a non-local partial differential equation holds at a point, this means that we also require value of the function, that is information in whole domain omega, whatever domain, in which domain we are considering our differential equation. The non-local partial differential equation which I am considering here, which that is given in equation number 1. And here the diffusion coefficient, we can see this diffusion coefficient m of L of u. This has basically two possibilities. L of u, either it can have like integral u dx, or it can be like integral mod grad u square dx. So because of presence of this term in this differential equation, this is no more a pointwise identity. That is why we call this equation as a non-local partial differential equation. So we know that getting analytical solution of these type of problems is a difficult task. Therefore, we need to consider some numerical technique for solving these type of partial differential equation. So the numerical technique which I will be considering here is finite element method. Here I would like to mention what are the why in particular I have considered this well-known method for solving this parabolic non-local problem. Basically, once we use this finite element method for solving this non-local problem together with the Newton iteration, the Jacobian matrix which we will get, that will not be a sparse matrix. That will be a dense matrix, and that will be computationally expensive. So also here we will tell what are the, how to overcome this difficulty. Is there any way to get a sparse matrix after applying the Newton's method into this parabolic non-local problem? So these actually issues I will discuss in my coming slides. So such type of equation basically appears in many real world phenomena. For example, this U could represent the density of the population of bacteria subjected to the spreading. Like that, there can be several applications. So now we will come to the weak formulation of given problem. Why we consider here the weak formulation of original PD? Because the steps in finite element method are as follows. First step is basically the weak formulation. So if I want to get the weak formulation of problem 1, we need to take a test function V in the Sobolev space at 0, 1 omega. This Sobolev space V consists of all square integrable function whose distributional derivative also belongs to L2 omega and V equal to 0 in the sense of trace on the boundary. So if we take that test function V and multiply our original equation 1 and then integrate by part, then we can land up into equation number 2. So this is our weak formulation. Before going into the finite dimensional setting, first of all, I would like to ensure about the well-posedness of this problem 2. For the well-posedness of this problem 2, we require certain assumptions on given data. So the first assumption is here given in H1, that is our initial data U0 is in H01 and F is in L2, L2. That means if we fix a time t, then this ft will go to L2 omega. Second assumption is m is bounded and it is positive also, strictly positive. We can see here positive, and also m is ellipsis continuous. So with these assumptions, basically we can show that there will exist a unique solution for this problem 2. Of course, from this we also can show that that there will exist a strong solution, and that will be also unique. And the method which we will use for solving the existence, for showing the existence and uniqueness, that is nothing but Galerkin method and compactness arguments. So now I will come to the finite dimensional setting, and here we discretize our space variable. So suppose we have a domain, in space we have a domain that is kind of a square domain. So what we will do here in semi-discrete formulation, we will actually divide our square domain into small triangles. So in each triangles, we have local degrees of freedom, and overall, if we consider this complete square, we will have global degrees of freedom. So corresponding to each global degree of freedom, we will construct linear hat basis functions. So how this VH finite dimensional space is constructed here? VH consists of all piecewise linear polynomials on each triangle, which will vanish on the boundary of the whole domain omega. That is how this space VH is constructed. So, so the semi-discrete formulation we will define with help of this space VH. Semi-discrete formulation is to find discrete solution UH in VH such that equation 4 hold. Now next we want to show that this semi-discrete solution is bounded. Also, because we have discretized our space, so that means we have incorporated certain error in our problem. So how much error is being introduced, that is also I want to discuss here. So in this a priori estimate, what I have shown that if f is in L2 L2 omega and UH0 is in L2 omega, then we have shown that this semi-discrete solution UH is bounded in L2 norm. Also, it is bounded in H01 norm. That is what we have shown in equation number 5. Now, in order to derive the a priori error estimate for this semi-discrete solution, we will be required this projection operator. This projection operator is defined here in equation number 6. This is known as the Rees projection operator. And with the help of this Rees projection operator, basically we have splitted our error U minus UH into two parts. That is rho and theta. So this rho is nothing but projection error, and theta is nothing but it is the discretization error. For the projection error, already we have estimates available in the literature, and they are given. Basically, these estimates are given in equation number 8, and references we have I have given here. So if we want to derive the a priori error estimate, I mean estimate E, then that means we just have to derive estimate for theta, because for estimates for rho are already available in the literature. So in the next slide, I will derive the estimate for theta. I will not give the complete derivation, just I will sketch the proof, that's all. So here, this is the statement of my theorem for the semi-discrete, for the error estimate for the semi-discrete solution. what here we have shown that if U is the solution corresponding to the weak formulation and UH is the solution corresponding to the semi-discrete formulation, then this error estimate which are given in 9 hold basically. So what it says that error in L2 norm, it is nothing but of order 2, and error in H1 norm, it is nothing but of order 1. So as I said, if we want to derive the error estimate, just we need to derive the estimate for theta. So we can show that the theta will satisfy this this equation, whatever I have written, this one. How to show that theta will satisfy this equation? This we can show just by taking the semi-discrete formulation and original weak formulation. From those two equations, we can derive basically this equation for theta. Now in this equation, we will apply Cauchy-Schwarz inequality, Poincare inequality, and also we use the property of our non-local term. Then we can land up into equation number basically 11. We can land up to equation number 11. And further, if we simplify this one, we can land up to equation number 13. So in this equation 13, we can see that the right hand side contains norm rho square plus norm rho s square. Already I told that this projection error is known to us. So we can use that projection error that is given in equation number 14. And finally, we can obtain the estimate for this theta in L2 norm. So L2 norm we have derived, it is of order 2. So ultimately we wanted to derive estimate for this norm of U minus UH in L2 norm. So this we can write it as, this will be less or equal to norm rho plus norm theta. And norm rho already we can see here, it is given in equation number 8. So norm rho we can use from there, and norm theta we have derived here in equation number 15. And we can add them up to get this estimate, which is given in equation number 9, that is estimate in L2 norm. Similarly, we can derive error estimate in H1 norm also, that will be of order 1. So till now we have discretized only the space variable, that is why we called it as a semi-discrete formulation. Now we discretize the space and time variable both, and we say it is a fully discrete formulation. So for discretizing the time variable, we use basically here backward Euler scheme. So this time interval 0t is divided into equal number of subintervals. That is, and each interval is having this length delta t, that is nothing but capital T by j. So with help of these notation, if U capital UN here, if this capital UN represents the approximation of this semi-discrete solution UH at time t equal to Tn, then if we apply the backward Euler scheme into our semi-discrete formulation, then we get this fully discrete formulation that is given in equation number 16. So fully discrete formulation is nothing to find here is nothing but it is to find capital UN in VH such that equation 16 holds. So now, as I said in the beginning, that if we, because it is a non-linear equation, so in order to solve this non-linear equation, first of all, we have to linearize it. So for linearization, we can use either Picard method or Newton method. Newton method has advantage over Picard method in the sense of rate of convergence. But if we use Newton method for solving this equation 16 together with finite element method, then what will happen? The Jacobian matrix which we will get, that will not be a sparse matrix. To see this, what we do, we again reformulate, we again reconsider this equation number 16 that is given in equation number 17. And now I will apply this Newton's method. So how we will apply here Newton's method? This solution UN, I will write it as, it is nothing but sum of U naught tilde plus WHN. U naught tilde is nothing but initial guess for the Newton iteration, and WHN is nothing but the correction term at nth iteration. So because UN I have considered here, so this UN I will substitute in this equation number 17, and then what we will get, that we will see in the next slide. Then finally we will land up with this equation number 18. So in this equation 18, we can see that this right hand side, This right hand side, this is nothing but the term corresponding to the, this is the equation corresponding to the correction term, that is WHN. And corresponding to this correction term WHN, the Galerkin matrix which we will get after using finite element method, that is nothing but it is given in equation number 19. And the right hand side term which we will get, that is nothing, that will be corresponding to this one. So now here I want to show that this Gij is not a sparse matrix. What I mean to say, what I mean by here is sparse matrix, a matrix which is having maximum basically 0 elements. If a matrix, if it is having maximum 0 elements, if elements are, most of the elements are 0, then we will say this matrix as a sparse matrix. So this corresponding to this term, phi, phi j. What are these phi and phi j? Phi and phi j are the basis function, linear head basis functions. They have compact support. And here I and j is varying from 1 to n. So this phi, phi j will give us a n cross n matrix. This will give us a n cross n matrix, but that matrix will be sparse. However, if we go into the second term, corresponding to this one, integral over omega phi separately, and this inner product, gradient u naught tilde into gradient of phi j. If we calculate this term, this second term, this will not give us a sparse matrix. Because of this term, basically sparsity of this G matrix is lost. So what will happen if I want to calculate this alpha from this equation G alpha is equal to R, then what we have to do, we have to get the inverse of this G matrix. And if G is a full matrix, then calculation of inverse of G will be computationally expensive. And this we want to avoid here. So how to avoid this difficulty? In order to avoid this difficulty, basically we will reformulate our original fully discrete formulation and then apply the Newton's method. So how we are reformulating? We are introducing here a new variable that is nothing here, that is D. And D I have written here, D is equal to integral u and dx. With help of this new variable, basically our fully discrete formulation can be written by equation number 21 and 22. Now in this equation 21 and 22, if we apply this Newton's method, then what? Then the Jacobian matrix which we will get will be of this form, that is given in equation number basically 24. This is here in J2. This is the Jacobian matrix which we will get when we apply Newton's method into our reformulated problem. So now I want to show that this matrix J2 is basically a sparse matrix. How it is a sparse matrix? So what are the entries of this J2 matrix? A, B, C and delta 1, 1, where A is given here and B is given here, C is given here and delta is given here. So from the entries of matrix A, that is AJL, they are of this form, phi L, phi j and grade phi L into grade phi j. Because phi L and phi j, they have compact support. So the matrix which we will get from this, these type of terms, that will be a sparse matrix. And obviously these Bj1, C1, C1L and delta 1, 1, they are just scalar or they are the row or column vectors. So that is how we have shown that theoretically that this matrix J2 is a sparse matrix. So mainly what here I have shown that this A matrix is a sparse matrix and hence J2 will be the sparse matrix. This also we will see in our numerical experiment. So as we have derived the a priori estimate and a priori error estimate for the semi-discrete formulation, same we will do also in case of fully discrete formulation. So the a priori estimate in fully discrete formulation, they are given in equation number 27. So in L2, in this equation 27, what we have shown that our fully discrete solution is bounded in L2 norm. And also it is bounded in basically H01 norm or in H1 norm, we can say, from this equation number 27. And about the a priori error estimate for the fully discrete solution, we have here this equation number 28. What it says that the fully discrete solution satisfies the estimate of this type. What is the meaning? That error in L2 norm in space variable is of order 2, and in time variable it is of order 1. And also error in H1 norm in space variable, it is of order 1. That is the second term. So this we will confirm numerically also. Means what I will show here? I will show that error in L2 norm is of order 2 and error in H1 norm is of order 1. This is what basically we will show here numerically. So for our numerical experiment, we have basically considered example where we know the exact solution, that is sufficiently smooth solution U. It is nothing but given here. With help of this exact solution U, we have calculated the right hand side F, and based on that right hand side F, we have used the finite element method for calculating the numerical solution. The domain, spatial domain, is taken to be square 0, 1, and the final time t at which we have calculated our numerical solution is t equal to 1. Also, the step size in time variable is taken to be 0.001, and tolerance for stopping the Newton's iteration is taken to be 10 to the power minus 15. The initial guess for Newton iteration is taken like 1 at the interior node and 0 at the boundary node. With these information, we have used finite element method and have obtained the following errors in L2 and H1 norms. So we can see that error in L2 norm is of order 2 and error in H1 norm is that is converging, that is convergence is of order basically 1 in case of H1 norm. Also, now I want to show the sparsity figure here. So if we use our Newton's method directly into our fully discrete formulation with finite element method, then the sparsity, we can show that sparsity will be like this. And that is, we can say this NZ represent here the number of non-zero elements in our Jacobian matrix. And if we basically reformulate our system and then apply the Newton's method, then sparsity can be shown by this figure. So we can say see that this one is sparse, however this one is dense, and hence it will be computationally expensive. So here I want to mention some possible extension also to this problem. Like here I have taken simple non-local parabolic partial differential equation. So here we can consider here in place of Laplacian term, we can have here P Laplacian term also, and even variable exponent problem also, Px Laplacian problem. So I mean those will be highly non-linear, and I mean that will require that may not be easy, but yes, I mean those also can be solved by using same technique. Yeah, thank you. So
yeah, thank you so much. Thanks, Sudhakar. Is there any questions?
Yes.
yes.
You mentioned sparse matrices. Now, are you aware of Nikhil Srivastava's work on sparse matrices? He did his PhD under Spielmann, and Marcus, Spielmann, and Srivastava solved Cardassian-Singer problem and got a lot of recognition and many prizes. Sparse matrices by Nikhil Srivastava.
Sorry, madam, but I mean I did not
Yeah, I'm just telling you. I'm telling you. It is
Okay.
not related to your work, but it is work on sparse matrices, and you are using them a lot, as I saw.
Yes.
Okay, so you might find some good results there to use.
Sure, madam. Sure.
Okay,
Yeah.
all the best.
Thank you.
Yeah, thanks, ma'am, for this nice comment.